In 1942, the industrial world entered a phase in which machines were no longer merely tools, but had become symbols of a nation's soul. Germany placed absolute faith in the concept of technische Überlegenheit, technical supremacy. It was not merely a production philosophy, but a religion of an empire that believed mechanical perfection could determine the fate of war. In the factories blazing with welding sparks at Kassel and Henschel, every screw thread, every bearing was ground to absolute precision. A German machine was not simply a weapon. It was a declaration of intellect and order. "We will win because we build better," said a panzer engineer in a 1943 interview record. That statement reflected the belief widespread throughout the Reich. Perfect engineering would triumph over numbers. From the 68-ton Tiger tank, the Me-262 jet aircraft reaching 870 kilometers per hour, to the V-2 rocket flying 320 kilometers, every project bore the same DNA, an absolute obsession with refinement. According to the Wehrmacht Logistics Office, 1,944, producing a Tiger tank required 300,000 man-hours and cost 650,000 Reichsmarks. That figure reflected not just expense, but a cult of craftsmanship. They were willing to pay an infinite price for precision. Across the Atlantic, America wrote a different equation. "Good enough wins wars," was the motto echoing through every production shift at the Detroit arsenal. For them, victory did not come from the strongest tank, but from the thousands of good enough ones rolling off the line each month. According to the U.S. Army Ordnance Department, in 1943, the Detroit Arsenal factory produced one Sherman every 60 minutes. At Willow Run, the B-24 Liberator assembly line run by Ford set a record of one aircraft every 63 minutes. When a Ford engineer was asked why they didn't refine it further, he laughed. "Perfection slows production. Soldiers don't have time for perfect." That philosophy created a system where efficiency defeated sophistication. Every Sherman leaving the factory was designed to be disassembled and repaired at the front line with a basic toolkit. Interchangeable parts, standardized bolts, simple welds. Nothing was exquisite, but everything worked. According to the 9th Army Logistics Division, more than 49,000 Shermans were produced between 1942 1945. In contrast, Germany completed only 1,384 Tiger I tanks during the same period. The disparity was not merely numerical, it was strategic. One side chose the perfect product, the other chose the indestructible one. That cultural gap was visible not only in the workshops but also in the engineer's state of mind. In Germany, the designer of the Tiger saw himself as a sculptor, with each detail embodying the beauty of precision. In America, the ordnance engineer viewed himself as a craftsman of the battlefield, tasked with ensuring the machine kept running through mud, sand, or snow. "We don't build heroes, we build tools," Life magazine quoted a production manager at General Motors in 1944. According to industrial historian Walter Dorn, World War II was a war between two engineering ideologies. Germany believed a perfect product could overpower the enemy. America believed a perfect production system could crush every individual product. From that point on, war was no longer a clash of armies, but a clash of two mindsets: engineering as art and engineering as logistics. When American supply ships docked in Liverpool, carrying hundreds of Sherman tanks and thousands of crates of spare parts, British officers remarked, "America isn't sending tanks, they're sending an assembly line." The statement was both admiration and prophecy. While the Tiger required a team of engineers to operate, the Sherman needed only a few soldiers to start it, replace the tracks, and move on. In 1944, analysts from the US, Army Ordnance compared the two philosophies in a classified report. German design optimizes the machine, American design optimizes the system. And in modern warfare, the system always triumphs over the machine. In the shadows of the Kassel factory, German workers continued assembling Tigers with microscopic precision. They did not know that in Michigan, a Sherman had just received its final coat of camouflage paint. Two machines born on two continents, carrying two opposing souls. one a monument to pride, the other a symbol of pragmatism. And somewhere between those factory floors, a new kind of war was being born. It was not about bullets or steel, but about the minds that made them. In World War II, engineers no longer stayed behind in the factories. They stepped onto the battlefield, carrying with them the philosophies, calculations, and convictions of the industries they represented. Every gear, every blueprint, every design decision could save or kill a company of men. The war of the 20th century was not merely a clash of guns, but a contest among those who best understood the limits of metal and time. And in that realization, the battlefield quietly shifted from soldiers with rifles to engineers with pencils. In August 1942, at the Henschel and Sohn factory in Kassel, the first Tiger I rolled off the production line. The 68-ton block of steel was considered the pinnacle of German engineering, the embodiment of the technische Überlegenheit philosophy, the belief that refined technology could substitute for numbers. According to the Waffenamt Prüfwesen 6 report, the Tiger was equipped with the 88mm Quak 36 gun, capable of penetrating 4 inches of sloped armor at a distance of 1,000 meters. At that time, no Allied tank could withstand a direct hit. In tests at Kummersdorf, the Tiger's PZG-39 shell pierced the Sherman's frontal armor like a knife through butter. To German crews, the Tiger was not a vehicle, it was a moving fortress. The heart of the machine was the Maybach HL 230 P45 engine, producing 700 horsepower at 3,000 revolutions per minute. Under ideal conditions, it propelled the 8.4 5-meter-long, 3-meter-high, 3.7-meter-wide tank at a speed of 38 kilometers per hour on level ground. The Tiger's ground pressure was only 14.8 pounds per square inches, lower than that of many light tanks, thanks to its large load-bearing wheels and wide tracks. That is why, in 1943 battlefield reports, Allied troops described the Tiger as a cathedral on tracks, a steel church that moved. But such greatness came with an enormous cost. Each Tiger consumed 650,000 Reichsmarks, equivalent to nearly 10 Shermans or 25 tons 34 seconds. According to estimates from the German Armaments Office, it took 300,000 man-hours to complete a single unit. The turret alone required over 1,000 mechanical components and 40 precision assembly steps. A German engineer recalled in his memoir, "A single bolt turned half a rotation off, and the entire transmission would jam." That statement was not an exaggeration, it was a fact. From bearings to pivots, every element of the Tiger was engineered for perfect balance. Yet in the chaos of war where mud, water, dust and rust met perfection became a luxury. The load-bearing wheel structure best exemplified the contradiction between theory and practice. Each side of the Tiger had 9 wheels, arranged in 3 interleaved rows to distribute weight evenly across the ground. This system made the tank move more smoothly, reducing vibration to the gun barrel and improving firing accuracy on the move. According to Krupp's 1942 design, this configuration reduced track pressure by 20% compared to simpler layouts. In theory, it was a mechanical masterpiece. In practice, it was a maintenance nightmare. To replace an inner wheel, the maintenance crew had to remove 8 outer wheels, each weighing nearly 80 kilograms. The task took more than 8 hours, even longer under battlefield conditions. In the mud of Normandy or the snow of the East, the 3-inch gaps between wheels often became clogged with stones, dirt, and even pieces of wood. Once something got stuck, the wheel stopped turning, and the stress on the axle could snap the torsion bar. Panzerabteilung 503's technical report, No. 178, recorded at least 23 cases of suspension failure due to foreign object wedged in interleaved wheels. German engineers tried to fix the problem by adding rubber rims, but the battlefield did not wait. When Tigers marched long distances across Ukraine or Normandy, the rubber wore out quickly and cracked in cold temperatures. Replacing rubber pads required dismantling the entire wheel assembly, a nearly impossible task under artillery fire. During the winter of 1943, many crews even lit fires under their tanks to melt the ice trapped between wheels. An image recorded in the field diary of Oberleutnant Franz Staudinger. We spent the night melting our own engineering miracle. The Tiger's operating theory demanded maintenance every 10 hours per 100 kilometers, oil changes every 500 kilometers, and constant checks of the transmission system. But in wartime, such routines were rarely possible. Wehrmacht supply lines were cut, fuel was scarce, and spare parts were insufficient. When a Tiger broke down in the field, repairs often took a week. According to a March 1944 report from the 2nd Panzer Division, only 43% of the Tigers in service were operational at any given time. The Tiger was born to conquer, but its sophistication made it fragile. In the dry environment of a test facility, it was a testament to German engineering prowess. On the muddy battlefields of Normandy, it became a vulnerable mass of steel. The interleaved wheels, once praised in technical drawings, turned into traps. An American officer wrote in a July 1944 battlefield report, "A perfect tank in theory, but in practice, it fights the terrain as much as the enemy." That perfection also created a psychological burden. Tiger crews were trained like miniature engineers. They had to understand the wheel structure, transmission system, gun pressure, and hydraulic controls. It took 6 months of training to be licensed to operate one. Many soldiers said that driving a Tiger was like marrying a machine powerful but endlessly demanding. When German engineers signed off on the Tiger's blueprint, they believed they were creating the perfect weapon, and indeed it was the pinnacle of engineering thought. But all perfection has limits. Normandy, with its thick mud, wire fences, and countless random elements, turned every strength into a weakness. In an ideal world, the Tiger ruled. In the real one, it fought not only the enemy but also its own sophistication. Perfection had weight, and for Germany in 1944, that weight was 68 tons. James Mallister arrived in Normandy with the second wave of reinforcements of the 1st Infantry Division. He was only 23 years old, formerly an electrician from Pittsburgh, Pennsylvania, where the hum of lathes and the smell of burning copper had followed him since his teenage years. When America entered the war, Mallister enlisted in the engineering corps, believing that his knowledge of wiring and current could help save lives rather than take them. But the European front cared nothing for ideals. In Normandy, the engineer's duty was not to design but to survive, clearing mines, building pontoon bridges, and clearing roads through fields littered with wrecked vehicles. He reached Omaha Beach on the 5th day after D-Day, amid rain and the stench of burnt smoke. Everything he had learned in the workshop no longer mattered. Electrical lines here were snapped, cables tangled in mud and blood. An officer told him, "In war, wire isn't for circuits, it's for survival." That sentence haunted him for months. He began to observe everything like a craftsman, trying to reconnect a broken circuit not with copper, but with instinct. In his first days in France, Mallister was assigned to a company tasked with clearing dirt roads around Carentan. According to the engineer logbook No. 14 of the 1st Division, the area had been devastated by retreating German tanks, many abandoned for lack of fuel. One morning, while inspecting heaps of wrecked steel scattered near an apple fence, he spotted a massive grey block of metal, a Tiger I tank, still intact, its hull covered in thick mud. The soldiers kept their distance, but he approached. Mallister climbed onto the hatch, placing his hand on the ice-cold steel. The feeling was unlike anything he had known. The surface was mirror-smooth, the welds neat, every joint fitted to perfection. He walked around the tracks, crouched, and studied the overlapping road wheels. 9 on each side, 3 interleaved rows, a maze of machinery. He began counting the gaps, measuring the distance between wheels with his finger about 3 inches. As he slid his hand inside, he felt rough scratches and torn rubber. There, a small stone was wedged between 2 wheels, crushed under the pressure of steel. He realized something that perhaps even the German engineers would not admit. This structure could devour itself. He knelt and examined closely. The interlocked wheels did not rotate freely but rubbed lightly against each other. Dried mud clung to the axles, tightening the entire mechanism. "This perfect machine is like an overloaded socket," he murmured. In Mallister's mind, the wheels became circuits, the torsion bars became wires, and the rotational force became a current blocked by resistance. He had dealt with hundreds of short circuits back in the Pittsburgh workshop, and always knew that no matter how strong the current, it could be cut if it hit the right point of resistance. Here, he saw the same principle. If a single hard fragment entered the gap, the whole system could stop. When he returned to camp, he drew a simple diagram in his notebook, rows of wheels interlocked like transformer coils. In the center, a small arrow labeled "Possible Jam Point." The paper was smudged by rain, but it would later become the foundation of one of the most improvised weapons in the history of military engineering. Within his unit, Mallister was known as a quiet man. He rarely told stories, preferring to observe. At night, while others played cards, he sat sharpening his shovel, watching the firelight reflect off the metal. A comrade recalled, "He watched machines like people watch fire." When he had spare time, he dismantled broken communication devices, reconnected wires, tested voltage, and drew schematics in charcoal on bunker walls. To him, war was a technical problem, placed in a random environment. During the weeks at Carrington, he saw all kinds of abandoned German vehicles, Panzer IVs, Stug 3s, and even burnt-out Tigers. He could never forget the feeling of touching melted rubber or smelling the scorched Maybach oil. The machine was powerful, yet it died from something mundane: lack of fuel, jammed tracks, broken axles. To an electrician, that was not a driver's error but a design flaw. According to records from the U.S. Army Corps of Engineers, on the 24th of June 1944, Mallister and the 3rd Engineering Team were assigned to clear obstacles along a dirt road between two villages near the Douve River. Along the way, he encountered two more Tiger wrecks, one abandoned in a field, another tilted into a ditch. He stopped to measure the track spacing and check ground adhesion. To other soldiers, they were just carcasses of tanks. To Mallister, they were open lectures. He discovered that the weakness lay precisely in what the German engineers took the most pride in: the perfectly balanced weight distribution mechanism. Everything in that machine was designed to bear load evenly, but a small deviation could make the entire drivetrain collapse like a shorted circuit. The thought lingered in his mind all night. "Every perfect system carries its own flaw," he wrote in his notebook. A simple line, yet it marked the transformation of his thinking from electrician to field engineer. He understood that war was not the place for ideal blueprints, but for improvisations made in seconds. His professional intuition began to take shape. When he saw a coil of telephone wire on the side of a truck, he thought of another use for it, not for transmitting signals, but transmitting force. If electricity can be cut off by a piece of wire, maybe this machine can too. The line was recorded by a comrade in a post-war report. It was the moment when a desperate invention began to take root. Amid the mud of Normandy, while other soldiers struggled to survive hour by hour, Mallister saw the world through an engineer's eye. Every malfunction was data. Every failure, a lesson. He did not yet know that those scribbles in his notebook would become the formula that could stop 56 tons of German steel in 2.8 seconds. And in that moment, the battlefield quietly shifted from a place of fear to a laboratory of survival. Before moving on to the next part, if this story resonates with you, please like and share so that more people can see it. Leave your comments below. Every word from you inspires us to create more great videos. On the morning of the 28th of June 1944, thick fog still covered the Carrington area. The ground was damp, the grass soaked, and the air heavy with the scent of burned metal. The engineering company of the 1st Division was holding a dirt road cutting through dense hedgerows, the only supply route available to German tanks. According to headquarters reports, at least 4 Tiger tanks from the Heavy Tank Battalion 101 were advancing northward. In the blurred light of dawn, Mallister understood that if those tanks broke through, they would sweep away the entire left flank of the American line. He had something no one else thought could be used as a weapon: 300 feet of braided steel telephone wire, the standard type used to connect command posts. The wire was 1/8 inch thick, with a tensile strength of 200 pounds, strong enough to pull a man out of a pit, but nowhere near enough to stop a 68-ton tank. To most soldiers, it was useless material. To Mallister, it was an experiment waiting to happen. He looked around. On both sides of the road stood the old fence posts of an abandoned farm. Amidst the overgrown grass, two massive oak posts still stood, each 18 inches in diameter, buried 3 feet deep in clay. He realized they were the perfect connection points, 2 poles in a natural circuit. He wrapped the wire around the left post 3 times, tied it with a triple fisherman's knot, then stretched it across to the other side and wrapped it 3 more times. When the wire was pulled taut 8 inches above the ground, it gave off a faint hum, like an over-tightened guitar string. Mallister stepped back, listening to the distant rumble of Maybach engines. The sound was deep and steady, like drums echoing from beneath the earth. According to Company B's log, at 6:18, the Tiger column began to move. He crouched behind the embankment, eyes fixed on a bend 30 meters away. The morning wind carried the smell of oil smoke. Metallic clanks echoed closer. Then the first silhouette appeared, a steel monster taller than a man, its 88mm gun turret slowly turning through the fog. The tanks advanced at just 4 kilometers per hour, their tracks grinding on the gravel. As the lead Tiger approached, Mallister held his breath. He knew that the wire could withstand only 200 pounds of tension, while the rotational force on the left wheel assembly exceeded 30,000 pounds. In theory, the wire would snap instantly on contact. But he believed in what theory overlooked: friction, wrapping, and the angle of contact. A light metallic snap rang out as the first wheel rolled over. The wire slipped between the second and third wheels precisely 3 inches apart, the fatal gap he had noted in his notebook. In a fraction of a second, the steel wire was drawn in by the wheel's motion, wrapping around the third wheel like a spool of thread. 3 turns, then 4, then 5. When the wire reached its limit, a sharp ping sounded not the noise of braking, but of tightening. Post-war engineering calculations estimated the torque generated at the binding point reached 2,000 Newton-meters, tens of times greater than the wire's rated strength. Yet instead of snapping, the wire was pulled deep into the gap, turning into a thin blade slicing through the rubber wheel rim. The torsion bar was forced off-center, and the suspension arm was bent. The entire left wheel assembly locked up within 2.8 seconds. As the right track kept moving, the Tiger lost balance, veered left, tilted 15 degrees, and came to a complete stop. The engine roared in vain, black smoke pouring from the exhaust. From his hiding place, Mallister heard a short shout in German, then silence. He couldn't understand the words, but the tone carried fear. As the first Tiger stalled dead in the road, the 3 tanks behind it stopped immediately. The road was too narrow to turn around, and on both sides stood high fences and soft soil. Any attempt to move would bog them down. Within a single minute, 4 machines worth over 6 million Reichsmarks were immobilized by a telephone wire weighing less than 8 ounces. According to the 1st Division's fire log, at 6:30, coordinates Carrington 1-4 were marked for artillery support. 3 105mm howitzers from Battery 32 fired the first salvo. Shells detonated 20 feet above the ground, raining steel fragments down on the accompanying German infantry. The survivors fled, leaving the Tigers stranded. By 7, American observers reported, "Enemy armor halted. Crews surrendering. IB." After the battle, Company B's combat report stated, "A communication wire, when properly tensioned, can disable heavy armor by mechanical jamming." It was the first time in the history of warfare that a wire designed to transmit signals had become a weapon of destruction. A soldier who was there later recalled, "The tank didn't explode, it just stopped. It was like watching a giant inhale and forget to exhale." That image spread throughout the regiment, a moment where mathematics, luck, and instinct converged. Mallister sat by the embankment, staring at the crushed wire still wrapped around the wheel. He said nothing. When an officer asked what he had used, he replied, "Just wire, sir." Throughout the morning, men gathered the wire and examined the site. An engineer noted in his log, "Suspension arm fractured, torsion bar cracked, both caused by asymmetric torque." These details were later included in technical reports from Aberdeen Proving Ground. Everything was measured precisely: one broken torsion bar, one bent suspension arm, 2 ruptured rubber rings, and an exact halt time of 2.8 seconds. By noon, the shelling had ceased. Through the haze, 4 German crews stepped out of their tanks, hands raised, their uniforms stained with oil and soot. The entire engineering company stood silent, staring at Mallister. No one could believe that a communications wire had defeated the mightiest machine of the Third Reich. From afar, Sherman crews began advancing, passing the Tiger tilted to the left. Mud splashed against its hull, and American tracks crushed the same road the enemy had held for weeks. One soldier murmured, "That's the sound of steel surrendering." In Mallister's hands, the remaining coil of wire was wet with dew and speckled with dirt. He ran his fingers along it, watching light glint off the thin steel. In his mind, every formula, every law of physics suddenly became simple: force, friction, and timing. Sometimes creativity needs no plan, only a moment of understanding the enemy better than they understand themselves. And in that moment, the war shifted. 56 tons of German steel bowed to a strand of telephone wire, and from the hands of a young electrician from Pittsburgh, the history of military engineering gained a new law. In the world of machines, sophistication can fall to simplicity. After the gunfire ceased, the Corentin area fell into an uncanny silence. The next morning, an American engineering team was dispatched to inspect the disabled Tiger. According to the U.S. Army Ordnance Service report dated the 29th of June 1944, the technical crew spent 12 hours removing the steel wire that had wound tightly within the wheel assembly. They had to use oxyacetylene torches, carefully cutting through each coil embedded deep in the layers of rubber and steel. When the process was complete, they recorded a detailed list of damage: 1 broken torsion bar, 1 bent suspension arm, 2 ruptured rubber rings, and 1 deformed bracket, all the result of a torsional force exceeding the design threshold. When the report reached higher command, engineers at the forward repair station could hardly believe it. According to the 1943 Henschel Technical Manual, the Tiger's suspension system was rated to withstand loads exceeding 30,000 pounds without failure. Yet at Corentin, it was defeated by a force generated from a 1 divided by 8-inch thick telephone wire. The entire crew sat around the tank, their hands covered in oil and iron dust, silently observing the jammed left track mechanism. "It's not the damage," one engineer said. "It's the principle." The remark was recorded in the inspection journal, reflecting the unit's astonishment. The most perfect German system had collapsed because of a simple mechanical reaction. The Tiger was later marked with white paint and transported to the U.S. Army Technical Center at Street Low for further analysis. The summary report stated that after replacing all damaged components, the vehicle could operate again. However, the chain of failures revealed a critical design weakness. By October 1944, the Tiger was shipped by sea to Aberdeen Proving Ground, Maryland, the U.S. Center for Testing and Decoding Enemy Technology. There, mechanical experts from U.S. Ordnance conducted dozens of measurements and concluded, "The interleaved wheel assembly of the Tiger creates multiple mechanical choke points when subjected to lateral torsion." These findings were immediately incorporated into training documentation. A copy was sent to the Army Corps of Engineers Command. In the conclusion section, it stated, "Single-point immobilization of armored vehicle achieved through passive interference, duration less than 3 seconds. Tactically, this meant far more than destroying a single tank. A Tiger stalled on the road became the choke point for an entire formation." According to the report from Company B, 1st Division, the 40-minute delay caused by the immobilized Tiger gave the Sherman Battalion time to circle and strike from the east. It was the first recorded instance of the delay to destroy tactic slowing enemy movement to create openings for mobile counterattack. After the battle, the company commander noted in his combat journal, "We didn't need to kill the tank, just to stop it." From a tactical viewpoint, Mallister's wire had not only halted a machine but disrupted the entire rhythm of a German armoured battalion's advance. According to the 9th Army Operations Report, July 1944, a Tiger column immobilized for 30 minutes on a narrow route incurred a tactical loss equivalent to 2 infantry battalions. In industrial warfare, time had become a new unit of lethality. The more sophisticated the system, the more easily it collapsed when thrown off balance. The Tiger at Carrington proved that truth, and in military academies it was later cited as the classic example of systemic fragility. The influence of the invention spread faster than expected. Mallister's report was forwarded to the Corps of Engineers Command, and by July 1944, the updated Field Manual No. 5-2-5 Engineer Field Data included a new subsection under Wire Entanglement Traps, detailing how to use field materials to disable armoured vehicles. From then on, engineering units in the European theatre were encouraged to carry 100-foot rolls of steel wire as standard issue. Of course, Mallister's success could not be easily replicated, but the idea itself changed how soldiers viewed creativity on the battlefield. Lieutenant Harry Dawson, commander of the artillery unit engaged at Carrington, recalled in a 1968 interview, "We thought it was luck, but command called it innovation under fire." The reports were sent to Washington, then to Fort Belvoir, the Army's engineer training center. Within 2 weeks, a replica of the Carrington Road was constructed, and the wire jam experiment was recreated under real conditions. Results showed that out of 5 trials, in 3, the wire wrapped around the tracks and brought the heavy M6 tank to a halt. However, the Germans did not remain passive. Starting in August 1944, the Wehrmacht High Command issued a new directive. Destroy any suspicious objects on the route of advance, particularly wires, poles, or communication lines. Each panzer formation was required to send a soldier 20 meters ahead for inspection, and machine guns were ordered to fire suppressive bursts at any suspect terrain. In Technische Dienstvorschrift Nummer 1944 section Panzerabwehrmaßnahmen, a warning was added: do not underestimate field improvisations. After these countermeasures were implemented, the wire trap tactic quickly lost its effectiveness. American engineers attempted multiple repetitions throughout September, but none achieved significant success. Nevertheless, the Carrington incident remained preserved as the first successful demonstration of passive mechanical sabotage, the destruction of mechanisms using non-explosive materials. A year later, when the war ended, the Tiger disabled by Mallister was displayed at Aberdeen with a plaque reading, "Captured in Normandy, disabled by field engineer improvisation." Under the fluorescent lights of the warehouse, the steel wire was coiled beside the massive wheel assembly. Amid footsteps and camera shutters, a young American engineer quietly read the inscription, 2.8 seconds to immobilize a 68-ton tank. In that moment, he softly said to his colleague, "It wasn't the wire that stopped it. It was the idea." And there, in the stillness of the testing hall, the war between 2 engineering philosophies ended with a simple lesson. The perfection of machines will always yield to the creative instinct of man. When American engineers at Aberdeen disassembled the captured Tiger piece by piece, they were not merely decoding a machine, they were witnessing a design philosophy pushed to its own breaking point. In the 1945 U.S. Army Ordnance Report, the very first line read, "The Tiger is a masterpiece of precision, and that is precisely why it fails." That remark summarized the greatest paradox of the entire war. Germany lost not because it lacked talent, but because it believed too much in perfection. An engineer from the Aberdeen inspection team recalled that to replace an inner wheel on the Tiger, they had to remove 8 outer wheels, each weighing over 80 kilograms, and the entire job took nearly half a day. Specialized tools had to be brought in from the Henschel factory, since even the Wehrmacht standard repair kit was not strong enough to loosen the layered bolts. Meanwhile, an American Sherman tank required only 20 minutes, and a common wrench set to change a wheel. In war, repair time equaled survival. A Sherman could return to combat the same day. A Tiger, if damaged at the front, was often abandoned. According to British Combined Intelligence Analysis, the monthly maintenance cost of 1 Tiger equaled that of 3 Panzer IVs. In other words, for every kilometre travelled, Germany consumed 10 times the logistical resources of the Allies. In industrial warfare, faster repair could matter more than thicker armor or stronger firepower. As one American officer said during the 1946 debriefing session, "Ease of repair is a weapon." That phrase became the new motto for post-war design generations. Numbers do not lie. Between 1942 and 1944, Germany produced 1,384 Tiger I, while the Soviet Union built 57,000 tons 34 seconds, and the United States rolled out 49,000 Shermans. The ratio of 35-1 favored the Allies completely. One nation built perfect machines, the other two built tens of thousands of machines that were merely good enough. While the Germans stopped to perform maintenance, their enemies were already sending hundreds of new tanks into battle. According to statistics from the 9th Army Ordnance Branch, during the Battle of Kursk in 1943, for every Tiger destroyed, the Wehrmacht spent an average of 200 maintenance hours and 3 days of resupply to replace it. Meanwhile, the Soviet Red Army needed only 30 hours of maintenance and 12 hours of resupply for a new T-34. The more complex the machine, the longer the supply chain, and that very chain became a strategic weakness. After the war ended, these lessons were systematized into a doctrine. At the first NATO conference in 1949, military engineers collectively approved a new standard known as crew-first design. This philosophy completely reversed the mindset of the 1,930 seconds. Instead of optimizing for armor thickness or mechanical precision, the priority shifted to crew survivability and maintainability under combat conditions. That is why post-war tanks, from the M48 Patton to the M1 Abrams, used fewer wheels, 6 per side, non-overlapping, replaceable within 15 minutes. Germany's later Leopard 2 followed the same idea, simplifying its suspension system and reducing parts count by 40% compared to the Tiger. The lesson of the Tiger extended far beyond tanks. It influenced aviation and the entire mechanical industry. When American engineers designed the F-86 Sabre, they noted in the documentation, "Maintainability equals flight time." Allied success did not come from miraculous inventions, but from the willingness to accept imperfection. They understood that in war, a system that fails gracefully will always defeat one that cannot afford to fail at all. By the 1,960 seconds, when U.S. military engineering academies revised their curricula, the Tiger Jam at Carrington incident involving James Mallister was included as a case study in applied field innovation. In lectures, instructors often asked students, "Why did the Tiger stop?" And the answer was never, "because of the wire," but rather, "because it could not fail gracefully." The German machine was built to function perfectly or not at all, while American design philosophy embraced controlled imperfection. According to the 1978 NATO technical analysis, the M1 Abrams could have its engine replaced in 30 minutes, a task that took the Tiger 48 hours. Such seemingly small details demonstrated the evolution of design philosophy since World War II. The simpler the machine, the longer it lived, the easier the repair, the stronger the army's endurance. The Tiger became a symbol of German engineering pride, but also an example of engineering irony, the paradox of sophistication. In a world where victory depended on speed and reproduction, perfection became a burden. A machine could achieve flawless precision in a factory, yet be powerless in the mud of Normandy. In the final assessment of the U.S. Army Technical Board in 1945, it was concluded, "The Tiger proved that mechanical perfection and battlefield survivability are inversely proportional." Germany triumphed in science but failed in practicality, and that lesson went on to shape the entire century of engineering that followed. Across the scrap-strewn fields of Normandy, the remains of the Tiger still lie silent, its interleaved wheels rusting in the grass. When it rains, water collects in those 3-inch metal gaps, reflecting the dim glow of sunset. It stands as a quiet reminder of what every military engineer knows: perfection is the most beautiful thing in the design room and the most dangerous on the battlefield. When the war ended, Europe was covered with twisted heaps of steel, the remnants of an era when engineering was used more to kill than to live. Yet among those burned-out wrecks were stories that still make engineers pause to think. One of them was the account of the young electrician from Carentan. The story of James Mallister was not just the achievement of an individual, but proof that the engineer's way of thinking could reshape the battlefield itself. The 20th century was the century of blueprints. From the laboratory in Peenemünde, where Werner von Braun calculated the trajectory of the V-2 rocket, to the Detroit workshop where Charles Sorensen optimized the B-24 production line, every engineer was fighting another kind of war, a war between models of thought. Each drawing, each mechanical diagram was a declaration of how humanity understood the world. The Germans believed in the supremacy of precision. The Americans believed in the power of adaptability. And between those two extremes, Mallister emerged not as a scientist, but as a practitioner, the one who proved that an understanding of matter could defeat an entire industrial doctrine. According to the Engineer Corps Review, 1,947 American military engineering schools began using the Carentan case as a classic example of field innovation under pressure. They called it the Mallister principle, the principle of creativity born from limitation. When interviewed in 1987, by then already retired, Mallister said a line still quoted among military engineers today. "I didn't think it would work, but sitting still would surely get me killed." It was not a boast, but a simple formula for creativity. People invent only when pushed to the edge of survival. In his world, a wire was no longer just a wire, but a conduit between idea and action. When asked whether he had planned it out, he replied, "I just saw the right moment, the right material, and enough desperation." The journalist who recorded that moment described him smiling faintly, holding a pen tightly, as if still calculating the angle of tension in that same wire. That humility allowed his story to transcend nationality. It became a story about how human intellect could turn limitation into leverage. At the Fort Moore Museum in Georgia, inside a small room dedicated to field engineers, there is a single glass case. Inside lies the steel wire, preserved in a vacuum-sealed box, its pale green insulation still intact. Under the soft yellow light, it appears ordinary, thin, rough, tarnished. But below it, a small plaque reads, "A strand of wire stopped 50, 6 tons of armor." No mention of victory, no medal, only a number and a cold conclusion. 1 wire and 50, 6 tons of steel. According to the museum guide, visitors often walk past the display without stopping. But every June, engineering students from West Point come and stand before the glass case for a few silent minutes. A professor once told them, "This isn't a weapon, it's an idea, and ideas don't rust." That single line captures why the wire remains preserved. It represents the triumph of the engineer's mind within humanity's most irrational setting, war. Mallister never saw himself as a hero. When asked about his feelings after the war, he simply replied, "I did what I knew best: observe, calculate, and attempt." Those last 3 words, observe, calculate, attempt, became the motto for generations of combat engineers that followed. Those who worked amid shellfire understood that no formula was perfect. Everything was an experiment fought against the limits of human endurance. Looking back, his act did not change the course of the war, but it changed how people understood the nature of engineering. It was not the art of making the most powerful things, it was the ability to find weakness within complexity. From that moment when the wire wound into the tiger's tracks, military academies realized that an engineer's knowledge could never be separated from the field. The difference between a factory engineer and a battlefield engineer lay in the presence of danger. One worked with materials, the other with time and survival. Decades later, that philosophy still holds. In the age of drones and cyber warfare, Mallister's principle continues to echo. No system, no matter how sophisticated, is without a flaw, and the engineer's duty is to find it before the enemy does. Just as the young electrician once saw not strength in the tiger's design, but a circuit waiting to be broken, Mallister's story was never about America's victory, it was about the triumph of simplicity over complexity. In the war between two kinds of engineers, one designing to dominate, the other creating to survive. The one who understood the limits of matter was the one left standing. When he died in 1989, the Pittsburgh Post-Gazette wrote in his obituary, "James Mallister, the man who stopped a tiger." But perhaps the truer description would be, the man who reminded the world that amid the echoes of artillery and shattering steel, the most powerful weapon is still the human mind. And in that silence, the war of engineers ended not with fire, but with understanding. The story of James Mallister and his slender wire has ended, yet its resonance continues in every laboratory, every workshop, and in the minds of young engineers learning to see the world through the lens of limitation and invention. A wire once stopped 56 tons of steel, but what made it immortal was the idea behind it, the belief that even the smallest fragment of knowledge can alter the course of an entire war. If stories like this make you reflect on the value of humanity in war and the power of intellect amid chaos, stay with us. Thank you for watching. We promise to bring you the finest stories. Don't forget to subscribe for more battles ahead.